The next topic in our chapter talks about drawing Lewis structures of molecules. The Lewis theory allows us to predict the distribution of valence electrons in a molecule, and they're useful for understanding the bonding in many different compounds, and eventually allows us to predict the shapes of molecules, the topic again that we'll be talking about in our next chapter. Looking at molecular geometry and thinking of a shape of a molecule not just as a flat two-dimensional drawing, but a three-dimensional figure in space. And knowing the shape of the molecule helps us predict properties of molecules and how they begin to interact with one another, the heart of chemistry. And it says, beware, it must be a warning. Lewis theory predicts that atoms will be most stable when they have their octet of valence electrons. We learned that as the octet rule. It does not require that atoms have the same number of lone pair of electrons they had before bonding. So always the primary goal is to get everyone the octet that it so desires. Some atoms commonly violate the octet rule, and the more we practice, the more that you generally see this. Beryllium, Be is this symbol. It's not the word be, but beryllium generally has two bonds and no lone pairs in its compounds. Beryllium is the first column in group 2A. Beryllium has two valence electrons. It will normally hybridize and just put an electron on each side and form two bonds. Boron generally has three bonds and no lone pairs of electrons. Boron lives in group 3A with three valence electrons. It normally will satisfy its shell with just three bonds. Beryllium will have two, boron with three. Many elements may end up with more than 8 valence electrons, and we'll see the examples called expanding your octet. They promote their p electrons into some empty d orbitals, spacing them out and creating an opportunity to put more atoms around the central atom other than 4. We expand the octet. Generally, trying to follow the common bonding pattern where carbon has 4 valence electrons. When I write carbon, I always place one around each side first, knowing that I see 4 places to bond. Nitrogen, which has 3 open spots for bonding with its 5 valence electrons, will show 3 bonds and 1 lone pair. Oxygen, who has 6 valence electrons, 2 open spots for bonding, so very common that it will have 2 bonds and 2 lone pairs. Hydrogen and the halogens, that's fluorine's family, fluorine, chlorine, bromine, who live in group 7A, will have 1 bond. Hydrogen has 1 electron. It will connect to form 1 bond. Fluorine has 7 valence electrons. It will connect to fill that empty space, 1 bond. So often Lewis structures with line bonds have lone pairs left off. Their presence is assumed from common bonding patterns. Now I like to show those because it helps us also predict the molecular geometry. You'll see me keep the lone pairs as we go through our examples. So just as what we drew together, here's boron with its 3. What's not included in this picture is beryllium with its 2, carbon with 4 bonds, nitrogen with 3, oxygen 2, and fluorine with 1. Thinking about the Lewis dot helps us to predict how many bonds will form. And we'll go through an example. Here's a molecule HNO3 we're being asked to draw. And I always pick the element that I have just one of and create that as the central atom. Never select hydrogen. Leave hydrogens for last, and they'll be like hole plugs. But I would select nitrogen to place in the center, thinking symmetry. I would not start hooking oxygens all in a row, but always connect back to a central atom. Hydrogen is always terminal. In an oxyacid, which this is, it's called nitric acid, hydrogen will attach to an outside oxygen. Leave hydrogen for last and plug a hole with it. Make the least electronegative element the central atom. The least electronegative element in this compound is nitrogen. We felt that it would be the central atom, Never pick hydrogen and pick the one that you have only one of. Count the valence electrons, says step 2. In nitrogen lives in group 5A, 5 valence electrons. Hydrogen lives in group 1A, 1 valence electron. Each of the oxygens, there's 3 of them, contributes 6 valence electrons for a total of 18. The total here that I'm allowed to use is 24 electrons. This is a way of checking that you've not gotten too many dots or not enough dots, representing the number of electrons. Sum the number of electrons so you can use a mental check to decide if indeed you've connected correctly. If you have a polyatomic ion carrying a negative charge, add those in. If you have a polyatomic ion with a positive charge, subtract those out. This is a gain of electrons. These are a loss of electrons. Adjust the number that you've totaled if it is indeed an ion. Step 3, now that we've calculated how many electrons we need to place, we start pairing them up. Don't forget a line represents 2 electrons. If I started with 24, I connect an oxygen. Don't forget each line is 2 electrons. What they're doing here is just starting to connect, so it looks like they're just rearranging and trying to find, and again, if I just started to draw, here's nitrogen with its 5. Place an oxygen to connect. That represents 1 from oxygen connecting 1 to nitrogen. So 1, 2, 3, 4, 5, 6, draw a line. 1, 2, 3, 4, 5, 6, draw a line. 1, 2, 3, 4, 5, 6, draw a line. We want to make sure that we have placed the oxygens around the central atom, leaving hydrogen for last. Now what I notice is that I have nitrogen with 3 single bonds, but I know I'm not done yet because I have 1, 2, 3 electrons that are unpartnered, 1 on each of the oxygens. Actually, the nitrogen looks fine, 2, 4, 6, 8, but I'm not done yet. I know that because I have a hydrogen to fill yet, and I have electrons that are unpaired on each of the oxygens. So really, that's what they've done for us here. They've completed the octets outside in. Hydrogen is already complete with 2, and they started to fill holes. Looking at that final structure that they're walking us through, they start to create double bonds. If all octets are complete, give the extra electrons to the central atom, and what you'll be doing is then expanding its octet. But if the central atom does not have an octet, bring in electrons from outside atoms to share, and just start thinking about the common patterns. Let's try drawing the following. Turn the video off and just take a practice. 1, 2, 3, 4, 5, 6 Lewis dot structures to draw. When you have a guess, turn the video back on and see if you've drawn correctly.